So in problem number 1, we have a cross-country runner who claims to be running exponentially faster over the course of the season. Let's see if that's really the case. So, her second race was at a speed of 10.71 kilometers per hour. Her first race was at a speed of 10 kilometers per hour. If we divide those out, we get 1.071. This tells us that her second race was at a speed 7.1% faster than first race. Another way to think about this is that the ratio between her second race and her first race is 1.071. So if her progress was truly exponential, she would keep up the same percentage rate of improvement across all of her future races. So from her second race to her third race, she would also get 7.1% faster. And from her third race to her fourth race, she would also get 7.1% faster. So this looks like a scenario for an exponential growth function. So we'll create our function f of x representing the speed in kilometers per hour of our Algebra 2 runner. And the initial value of the speed is 10 kilometers per hour. And the rate of change is 1.071. In other words, if she truly was exhibiting exponential progress, each race would be 107% of the speed of the previous race. In other words, a 7.1% increase. So our exponent here would be x. So now we can graph this and see what would happen after 12 weeks. You could also plug this into your calculator and find f of 12. So find what her speed is equal to when we plug in 12. 10 times 1.071 to the power of 12. But let's plug it into Desmos and see what we get. Here we have 10 times 1.071 to the power of x. Notice how here the graph starts, it intersects the y-axis at y equals 10. So the initial speed after 0 weeks have passed is 10. Notice that after 1 week, she is at about 10.71. Specifically, we want to find out what happens after 12 weeks. So I'm going to graph the line x equals 12. Where this intersects our exponential function is where our runner's speed will be after 12 weeks. So as you can see, this is at the point 12, 22.7. What this is saying is that after 12 weeks, if her progress was truly exponential and her speed increased by 7% every week, then her speed after 12 weeks would be 22.77 kilometers per hour. This is very fast, 22.7 kilometers per hour. Converted to miles per hour, we would divide by approximately 1.6, which is the number of kilometers per mile. It's about 14 miles per hour. It's a very fast pace to run a cross-country race in. So I'm going to write approximately equals 22.77. Now to convert this into the time that it would take her to run a 5K, we can take the distance 5 kilometers and divide it by the number of kilometers per hour to get the number of hours that she would run 5 kilometers in. So going back here, we could take 5 kilometers and divide it by 22.7. And we get 0.219. So what this is saying is that at that speed, it would take our runner about 0.219 of an hour to run the 5K. So a little more than a fifth of an hour. So this is going to be a little more than 12 minutes, an extremely fast time for a high school cross-country runner. So if we take 0.219, multiply it by 60 to get the number of minutes in an hour, we get 13.14. So she will run the race in a little over 13 minutes. Problem number 2. You have $1,000. You are offered an investment account that either A, guarantees a flat return of $50 per year, or B, a return of 3% per year, with interest compounded annually. Okay, so we need to compare two different functions here. The first function is a linear function. F of x equals 1,000, which is the initial investment, plus a constant return of $50 per year. So we have our initial investment, 1,000, plus $50, which is the annual return, times x, which is the number of years. On the other side, we have a different function. This is going to be an exponential function rather than a linear function. Here we have $1,000, which is our initial amount, times 1.03 to the power of x. The reason we have 1.03 is that we're using our formula for exponential growth, where we take 1 plus the rate of change for growth, which is 3% or 0.03. Now, another way to think about this is that every year in this account, you have 103% of what you had the year before. So in year 2, you have 103% of what you had in year 1. In year 3, you have 103% of what you had in year 2, and so on and so forth. So after X years, you're going to have 1,000 times 1.03 to the power of X. Now, it's not immediately obvious which of these two functions is better for 10 years and for 40 years. So we're going to graph these two to see how they compare. So our first function is going to be 1,000 plus 50 times x. Notice that we might have to change our axes a little bit on Desmos. So here we want to zoom in on the interval that we care about, which is between 0 and 40 years. And our second function was 1,000 times 1.03 to the power of x. Okay, notice what happens here. After 0 years, they both have $1,000, no return on investment. For the next approximately 30-something years, the flat rate is preferable. The flat rate will give you more money than the interest rate. However, after about 32.9 years, the interest rate begins to be the preferable option. And by the time you reach 40 years, let's say we draw a line at x equals 40, you can see that the interest account will have $3,262 versus only $3,000 in the flat rate account. So after 40 years, having the interest rate will get you a profit of $262 compared to the flat rate. And you can see that this difference will only increase over time. So the answer, going back to our problem, would be that it would be wiser to pick the flat rate of $50 per year if you're only investing for 10 years. But if you're investing for 40 years, it would be wiser to pick the 3% per year interest rate account.